For those of you that don't know me, I am the son of Dr. Herbert Nagasawa, who inspired me to help him commercialize RiboCeine. And this is the reason why I'm here today. This year, we'd like to do something different and have invited some notable guests to be part of a panel discussion on glutathione, which I think you're going to really appreciate. Our first guest is a very special individual, Dr. Jeanette Roberts. Dr. Roberts received her PhD in medicinal chemistry at the University of Minnesota, and her thesis to get her PhD was on D-ribosylcysteine, or ribosine. As a graduate student, my father told me that she had straight A's and was one of the brightest graduate students that he has ever had. And it's no surprise that she became dean at the University of Wisconsin School of Pharmacy. She was also associate dean here at the University of Utah and is responsible for publishing many of the RiboCeine papers. Our second guest, Dr. Sally McCormick. Dr. McCormick Dr. McCormick is an associate professor of biochemistry at the University of Otago. And she comes here all the way from New Zealand to attend this event. And many of you here, including myself, know that this is a very long flight. Well, this summer, Dr. McCormick was invited to do an oral presentation at an international conference that was held in Paris related to her research on RiboCeine. And yesterday, at the medical symposium, she shared these findings with us. Also part of the panel will be my father, Dr. Herbert Nagasawa, and of course, Scott Momey. So please provide a warm welcome to our panel guests, Dr. Jeanette Roberts, Dr. Sally McCormick, Dr. Herbert Nagasawa, and Scott Momey. So what do you think about our panel guests? Well, let's go ahead and get started. I often get asked the question, why glutathione is considered the master antioxidant. In your opinion, why does glutathione deserve this unique distinction of being the master antioxidant?
It's quite amazing to continue to discover the many biochemical processes and disease states in which glutathione plays a positive and protective role. So as this list has gotten longer and longer, it's very appropriate to consider glutathione the master antioxidant. It's also called the maestro of the immune system, which I think is equally valid. The connection to the ribosine technology is important, of course. Glutathione itself is a simple tripeptide, meaning it's composed of 3 amino acids, with the cysteine molecule being the workhorse of glutathione. And due to its chemical properties, the cysteine part of glutathione is able to chemically combine with a variety of very reactive, toxic molecules in the body and detoxify them in that way. It's also a powerful free radical scavenger. So in situations of oxidative stress, in the presence of reactive oxygen species, it can detoxify those free radicals as well. So it can do this through 2 mechanisms, and combined with the feature that it's involved in so many important biochemical processes and is depleted in disease states, it really is the master of the antioxidant universe.
Dad, a question for you. Why is cysteine so important for glutathione production? And what makes RiboCeine so unique in your opinion?
Well, as Dr. Roberts has so elegantly described, cysteine is the absolute requirement for the production of glutathione. The problem with cysteine in the body is that the cysteine concentration in cells are kept at a very extreme level, low, very low level, whereas the other two amino acids, glutamic acid and glycine, have ordinary levels. Therefore, cysteine absolutely has to be there in order for glutathione to be produced. And this is why we call cysteine the rate-limiting amino acid for the biosynthesis of glutathione. Now, this is why we target cysteine and try to get cysteine into the body in bioavailable form. Because one cannot just take cysteine itself, the molecule cysteine itself, because that cysteine is not bioavailable. Now, there are now two bioavailable cysteines. One is N-acetylcysteine, NAC, as you well know about that, and a second one called ribocysteine, or ribosine for short. And these are the two now bioavailable cysteine molecules, and the second one, ribosine, is a more modern version of the first. Now, why is ribosine so different? Well, as Dr. Roberts said, it was designed that way. It was not an accidental discovery. It took many, many years to discover it, to get to that stage, and many pitfalls, pitfalls. We had many obstacles. Finally, we did actually synthesize the molecule and show that it was a good one. The reason why ribosine is so unique is that it is not cysteine itself. If this is cysteine here, molecule of cysteine here, and this thumb here represents the sulfhydryl group, or the SH group of cysteine that she said was very important in terms of glutathione trapping free radicals, etc. What we have done is take that sulfhydryl group on here, SH group on there, and covered it up with a molecule, another molecule, and that other molecule is ribose. Now, the beauty of using ribose as a cover-up molecule is that ribose is already in your body. You get it from glucose. It's a metabolized glucose. So the ribose condenses with the sulfhydryl group of cysteine. In the process, water is lost, and then you have a new molecule called ribocysteine. Entirely a new molecule. It's no longer cysteine, but a new molecule called ribocysteine, and ribosine for short. Now, when you have this molecule, now you have cysteine stabilized, and you can take it orally, goes into the stomach, which is very acid, perfectly stable, and travels through the intestine into the organ, and then gets into the cell. Now, once in the cell, this molecule ribosine spontaneously and non-enzymatically and slowly releases cysteine by a process known as rehydration or hydrolysis. Water enters the system again, this molecule again, and then breaks it apart, and you have cysteine now inside the cell as well as ribose inside the cell. So what we have is a very unique molecule, ribocysteine, that you can take orally and get traversed system and get delivered to the cell. So this is why ribosine is such a unique molecule. Now I hope that you've now understood. You now understand the science behind ribosine.
Dad, early on, you told me you wanted to see ribosine available throughout the world. What was your reason for that?
Well, I thought about that, and that's why we designed ribosine in that manner. Because if you want to have a molecule that has important as ribosine, you want it to be taken by everyone. Everyone that needs it, everyone that wants it to maintain their health. And this doesn't include just the people in the modern world, but also United States, I should say, in the United States, but also throughout the world. Because glutathione deficiency is not just confined to the people in the United States, it's to the population of the whole world. And I am very happy to learn that Max International, true to its name, International, has now taken ribosine to the far corners, like in Africa, South America, and Far East Asia. and I applaud Max International, which means all of you here, for doing this. Thank you very much. However, I have another wish, and this is a vision of sorts. I would like to see Max International as a corporate policy. As a corporate policy ingrained in the concrete, to take a small fraction of the total production of ribosine and set it aside and then offer it, donate it without charge to the very, very poor in the less developed countries.
Your dream's gonna come true. I got permission from our CEO to open my mouth, and we will take and donate where we are able to in the countries that we can legally do it in. We will start making those donations this year. Because of you. If it wasn't for what you do with your teams, there would be nothing to give. And Joe, Dave, and I, Shannon, Jim, the entire Max team understand who is responsible for Dr. Nagasawa's dream being true. And we are so grateful to you. And I'm on this stage for the very first time. I've never shared a stage with any of these people, but they're my heroes.
Dr. McCormick, yesterday you had an opportunity to speak at the medical symposium regarding your research on ribosine, specifically the importance of glutathione in protecting our cardiovascular system. Can you discuss your research maybe in simpler, less technical language than yesterday?
Sure.
Is that possible?
The audience will appreciate that, I'm sure. So we performed an animal trial on ribosine, and my lab's interested in atherosclerosis, which is a process that underlies cardiovascular disease, and we're particularly interested in the lipid risk factors for cardiovascular disease. You all heard about the bad cholesterol and the good cholesterol and their role in promoting or protecting against heart disease. We decided to test ribosine in an animal model. It was a mouse model. It was a model that had been engineered to have a lipid profile that was very much like humans. So mice don't normally get heart disease, and part of the reason for that is they have what we call an HDL, or a good cholesterol lipid profile. But we have a model that's been engineered to have high levels of the bad cholesterol, which is the LDL cholesterol. That's the one that you don't want to be too high when you get your lipid test. And the animals also, besides having high LDL, they also have another lipoprotein, another lipid molecule called lipoprotein a, which is also, like LDL, a very important risk factor for developing heart disease. So we wanted to test the effect of ribosine on these lipid levels, and we were also interested in looking at the effect of ribosine on oxidized lipids, which is another risk factor for the development of heart disease. So we got on the phone or the email, and I consulted with Scott about the design of the study, which was very important in terms of the dose that we were going to give the animals and how we were going to give the ribosine and for how long. And we came up with a design which had us giving the animals 4 milligrams per day for over 8 weeks, for just on 8 weeks. That dose is about 0.16 grams per kilogram. A little bit higher, that's what's in the Max 1 product. And so we undertook this study. We gave the animals the ribosine in their drinking water. It was funny, when I was doing the study, my students kept asking me, I wonder what it tastes like, you know. And they were wanting to dip into the ribosine bottle and drink it, mix it up with water and drink it. But I said, no, come on guys, we've got to wait till we've finished and got the results of the study before we do that. And so at 8 weeks, we harvested both the liver and the blood of the animals, and we first looked to see the effect of glutathione. And as we hypothesised, of course, that ribosine would increase glutathione levels, and that in turn would increase the level of a very important antioxidant enzyme called glutathione peroxidase. And glutathione peroxidase needs glutathione as an important cofactor. It's an absolute requirement for its activity. And the role of the glutathione peroxidase enzyme is to reduce oxidized lipids to a less toxic product. And so we hypothesised that we would see an increase in glutathione, we would see an increase in glutathione peroxidase activity, and that would lower the level of oxidized lipids in our animals. Lo and behold, when we looked at the results, we saw an increase in glutathione in both the liver and the blood of the animals. We saw an increase in the glutathione peroxidase activity, just as we predicted, both in the liver and in the blood. And last but not least, we also saw a decrease, quite a significant decrease, in the level of oxidized lipids in both the liver and the blood, and also in the arteries of the animals. We actually looked at the level of oxidized lipids in the arteries. And it's in the arteries where oxidized lipids actually promote the inflammatory events that promote the development of heart disease. So we're really quite excited about those results. We then went on to look at the plasma lipids, and we didn't know what effect ribosine was going to have on the plasma lipids, but we knew that other antioxidants did affect plasma lipids. And to our surprise, we found that ribosine significantly lowered LDL cholesterol, which is the bad cholesterol that's involved in the development of heart disease. We also found that ribosine lowered lipoprotein little a, which is another atherogenic lipoprotein involved in heart disease. And it did this without altering the good cholesterol fraction, which is the HDL fraction. That seemed to be unaltered by ribosine at all. So overall, quite significant results. We've since gone on, actually due to the comments by the reviewers of our paper, to look at the mechanism underlying the LDL cholesterol lowering, and we've got some preliminary data that shows that ribosine actually increases the expression of the LDL receptor, which is a key molecule in lowering LDL cholesterol. It's the receptor that is expressed on all our cells that binds LDL from the blood and takes it up from the bloodstream. And so we think that is the way in which ribosine is working. A wee bit similar to a statin drug, which you guys are probably familiar with, which is a major cholesterol lowering drug. We've still got a little bit of work to look at the mechanism, but that's our findings so far. We're really quite excited about what we've found. Of course, this is in mice, and we need to look at it in humans to really prove that what's going on, but that's what we found.
Thank you for that very simple review. Dr. Roberts, do you have any final comments before we conclude?
Well, it's amazing to think that 30 plus years ago, this work started under the direction of Dr. Nagasawa, and that it can take that long to accumulate the appropriate evidence, generate the appropriate manuscripts and collaborations. And I think it's simply a lesson in perseverance, if nothing else. But I have to tell you how deeply moved I am by where ribosine is at this moment, due to the work of Max International, all of you, Scott and Scott, all the scientists around the world that are looking at its beneficial effects, and of course, to my mentor and colleague, Herb Nagasawa, for the opportunity to work on this project. Thank you.
Dad, do you have any final comments?
Yes. I'm very happy. I'm very happy that all of you here, the Associates of Max International, actually has now met the people here who actually did the work and are doing Dr. Roberts did a lot of work on ribosine, and now Sally's taken over and doing even more important things on ribosine. I'm happy that you're now able to meet them.
Well, thank you very much. That concludes our discussion on glutathione.